Okay, so we're going to go translations of functions. Now, what they mean by translations of functions is it means we can have any function, and that's what this f stands for, and these rules that we're about to figure out for these variables a, k, c, d, and some books have different names for them, will always work no matter what the function is, okay? So one of the functions that you tend to have worked with in the past is a quadratic, x squared, but this will also work for something that's cubed, or if it's rooted, if it's the absolute value. What else? If it's a reciprocal function. These rules work for all of these different things, and each of these create a different shape on the graph, okay? Now, the first one we're going to talk about is A. A deals with vertical stuff, so I'm going to draw lines that go up and down. That means it deals with vertical, in this case, stretches or compressions, okay? So A, if A is a value that's greater than 1, they call it a vertical stretch. Okay, that's what happens to it. They call it a vertical stretch. And if A is a value that is less than 1 but still greater than 0, it's a vertical compression. Okay, so what they mean by that is, and we'll draw it on a graph in a second, is that you're going to take that function and you're going to pull it much longer from the top. So one function that it actually really works well with is, an example of it is with like a quadratic, okay? So quadratics normally look like this. If our A value was greater than 1, think of it like an elastic band, and it would get pulled up. And that's what they mean by stretched. We're pulling on it upwards, okay? Well, that same idea, if it's between 0 and 1, it's compressed, so it gets wider, is what we're talking about, okay? It's as if something is sitting on it. So one way we tend to think of it is pretend this is our line. If we're stretching it, that's when we're pulling this line upwards. And think of it as if it's attached to this line, these points here. So as we pull it upwards, you'll notice that it gets thinner, right? So as we pull this bar upwards, this thing gets pulled inwards and inwards. And if we were to do the opposite with that bar, it would get wider and wider, as if something is crushing it. That's if we're pushing the bar downwards, okay? And that's what these numbers essentially do to the function. So that's just to get a general idea of what it's going to look like. And then there's also something when A is a negative term, okay? It's flipped, spell that right, flipped on the x-axis. And what that means with a quadratic is, think of it like this. We take the original, and if A is all of a sudden negative, it no longer opens upwards, it opens downwards, okay? So those are the rules for A. A quadratic's a nice one to work with for A. Now K is a little harder to work with a quadratic, so we're going to use a different function to represent it. It's still the exact same rule. K actually deals with horizontal stretches and compressions. So they deal with the same types of stuff, but instead of going up and down, this one goes left and right. Okay, so our rules for K, if K is greater than 1, it's actually a horizontal compression. Okay, and what that means is essentially it's the opposite of what our A is. Okay, and we're going to figure out a rule with that, and I'll show you what I mean by that. If K is between 1 and 0, so if that number is between 1 and 0, it's a horizontal stretch, which is the exact opposite of what we just said for our A value, if you notice, right? We said when A is greater than 1, it's a vertical stretch. Well, here when K is greater than 1, it's a horizontal compression, different type of term, okay? A good function to work with when talking about that one is our root function. Okay, I'm going to write it actually in black. Here's our root function. Have you seen this function before? Mm-hmm. Okay, and the way they usually represent it is with something like this, right? I want you to think of that same idea as we had before. Imagine, I'm going to move it over a little. Imagine he is attached to a, in this case, you remember we had a horizontal line with the A and we were pulling it up and down. In this case, I want you to think of it like we have a vertical line, Okay, so we have a vertical line that it's attached to. And when k is greater than 1, we push that vertical line this way. And what ends up happening is we get a function that kind of goes, it gets pushed upwards. Okay, kind of makes this. Think of it as if it's being crushed, so it's being pushed in this way. Okay, this is our horizontal compression. It's getting squished from the sides. Okay, and a horizontal stretch would be if we were taking that line and we were pulling it farther. If we were pulling it farther, what we're going to end up getting is something like this. We're just going to get pushed all the way out here. Okay, so it's getting pulled that way. So this way is a compression, and this way is a horizontal stretch. So these things create similar movements, A and K. They're just kind of opposite of each other. Okay, because A also affects this type of function also, and we'll get more into depth with that. I just want to give you the idea so far. Okay, so I know it's hard to idea, but think if we're squishing something for A from the top and the bottom, so we're pulling it up or squishing it down. And for K, it's like we're taking from the left and right and we're squishing it inwards, or like an accordion, pulling it outwards. That's the effect it's going to have. Now there's two other ones. These ones are actually a lot easier to work with. I kind of drew underneath them. But C also deals with horizontal stuff. I'm drawing left and right, so we know it's horizontal. And it has to do with moving the function, the entire function. Okay? So in this case, if C, oh, you know what? Sorry, I did forget one last thing. For K also, if K is a negative, K equals a negative term, it's also flipped, but it's not on the x-axis.
It's on the y?
Yes. Good. On the y-axis. Right? So in which case, our original one kind of goes like this. And if we flip it, it goes the other way. That's what that happens there. Okay? So we've done with the three major rules. These are the hardest ones to deal with, are A and K. C and D deal with moving the entire function at the same time. So if C is, excuse me, if C is a negative term, we move in a positive direction. It's kind of the opposite of what you would think. Okay, so if it's negative, we move in a positive direction. So in this case, that would be to the right, because it's horizontal. Right? Because we're talking about how this moves horizontal, we'd move to the right. If C is a positive term, we move in a negative direction. Exactly. We move to the left. And what we mean by that is, again, we'll use a quadratic for this one. It works for all functions, okay? But if C is negative, the entire function gets shifted. It's still the exact same shape. The shape doesn't change. It just gets moved one way. Okay? And the opposite, if C is a positive, the whole function goes the other way, being the same shape. Those are the only two rules for those ones. Okay, so you just got to look at what operation's in front of it. And finally, D, we'll jump back up. And once we do an overview of this, it'll make a little more sense. As again, vertical stuff. So I want you to notice the pattern also. Everything in the brackets is horizontal stuff. Everything outside of the function, so like A was outside of this function and D is added or subtracted at the end, is vertical stuff. Okay? And D is the same type of thing as C, except it actually kind of makes sense. If C is positive, we go in a positive direction. We go up because it's vertical. Okay? And if D is a negative term, we go in a negative direction.
Would it still be turned up, or would it have to go down?
It would still be facing the same way. The only times the facing changes is flips. So that's only when A or K are negative. These terms just deal with moving the whole thing left and right and moving the whole thing up and down. So for instance, we'll do another, in this one I'll use a root function. Okay? So if I have my root function, it starts here. If it's a positive term, the root function just gets moved up. Still facing the exact same way. Okay? And if it's a negative term, that root function, still facing the exact same way, is just shifted down the graph. Okay? So here's a general overview. So those are all of the rules. Okay. What we're going to start to do is we're going to apply these to specific functions so we see what happens to them. Okay. Let's see how long we're going here. That's 10 minutes, so that's probably about good. So these are all the rules. What we'll do is we'll print this out, and then we'll go through some questions using them. Okay.